Welcome viewers back to this course. So, in the last class we have started with the Laplace transformation and then we have discussed the existence for the Laplace transformation. So, these were the slides which were the last slides in the previous lecture. So, in that the m was skipped. So, this m is also there. So, you just correct that this m is there and then other things are same. So, now we are going to start with the next lecture and that is the lecture number 15. So, in this case also we will discuss the various properties of the Laplace transformation. So, in the last class also we have discussed that if my function f t is 1 by t. So, in that case we have found that the Laplace transformation does not exist. So, this one we have discussed in the last lecture. Now, what about, so if you see this one, I can say that from the existence theorem, my function 1 by t is like this one of this type, never touching this t axis, and this my f t is equal to 1 by t. And if I take the any exponential function for any value of alpha, that is always of this type. So, if you see that at this point after this value, this function is satisfying that this my function f t is equal to 1 by t is of exponential order, but as we are going close to 0, it is unbounded function, and in that case we say that this function f t is not of exponential order. And then in that case, and also in the Laplace transformation we are dealing with from 0 to infinity. So, this function is unbounded as we go close to the 0. So, for the integration actually we have to see that if I take the Laplace of 1 by t, then we have to see that from 0 to infinity e raised to power minus s t over t dt. So, how this behaves when we are going close to 0. So, that is the main thing. So, in this case we say that the Laplace transformation does not exist. But if I take the another function of the similar way of 1 over under root t. So, let us see that this function is also of this type. If I plot this function, only thing is that this function is falling much slowly as compared to the function 1 by t. So, we want to see that how it behaves when we multiply by e raised to power minus s t near 0, because the function is the problem when t tends to 0. So, let us take the Laplace transformation of this function f t over 1 by under root t. So, let us take the Laplace transformation this one. So, this is from 0 to infinity e raised to power minus s t over under root t dt. Now, I will take the variable change of variables. So, let us assume that my s t is some w I take. So, from here I can say from here that the t is w by s. So, from here and also my s dt is equal to dw. So, from here I can define my function is equal to, and when t equal to 0, w is also 0, when t is equal to infinity, the w is also infinity. So, from here I get my integration from 0 to infinity e raised to power minus w. So, this is the w I have taken dt is dw over s and under root t. So, under root t from here, my under root t from here will be, so under root t will be w by s. So, from here and this one, so I can write from here. So, t will be this one. So, from here this can become 0 to infinity. So, under root s, and because I am taking the integration with respect to w, so s I can take common. So, it will be under root s over s, and inside it is minus w by under root w dw. So, this becomes 1 over under root s 0 to infinity e raised to power minus w over under root w dw. And this one again I can write in this form as taking the change of variable. W is equal to, I can take as x square, and from here I can say that dw will be 2 dx, right. And then from here the integration is same, when w is 0, x is 0, when w is infinity, x is infinity. From here I can write as 1 over under root s, and the integration from 0 to infinity e raised to power minus x square, and under root is x, and from here dw is 2x dx. So, this will cancel out, and from here I can write that this is equal to under root s from 0 to infinity e raised to power minus x square and dx. And you know that what is this? So, it is the Gaussian function. Gaussian function, and I know that from the integration, that if I take the integration from minus infinity to infinity e raised to power minus x square dx, then it is equal to under root pi. So, from here I can say that, and this function is always positive function, and this is a symmetric also. So, from here I can say that this will be equal to, the integration of this one will be equal to, from, because this is given from minus infinity to infinity, but here in this integration is from 0 to infinity. So, from here I can say that this is equal to under root pi by 2. So, this 2 will cancel out, and from here I can write that this is equal to this one for s is greater than 0. So, from here I can say that the Laplace transformation of the function f t is equal to 1 by under root t is equal to pi over s when s is positive. So, in this case the Laplace transformation exists for 1 by under root t, because I told you that it depends upon that how the function is behaving when we multiply with e raised to power minus st near the point t equal to 0. So, from here we are able to see that the Laplace transformation of the 1 by under root 2 is under root pi by under root s when s is positive. So, now we will define some another properties of the Laplace transformation, and that another properties the Laplace transformation is, the first one is that if my function f t is there, and I already know the Laplace transformation of that function f s is given. So, what will happen sometimes that I have multiplied by this function f t by some exponential a t f t. So, what will happen there? And then we, from here, just I want to find the integration e raised to power minus s t e a t f t E, so this is f t dt, and which can further be written as E minus s minus a t f t. And from here I can say that this is again the Laplace transformation of f t, only thing is that we have changed my s to s minus a. So, from here I can say that this is the Laplace transformation with the change in scale of the s. So, here we have written that f is s minus a. So, we are changing the scale of the function s by the a. So, from here I can say that the Laplace transformation of E a t f t will be f of s minus a. So, I am changing the scale. So, like I can define now that if I take the function f t and this is my s and this is my f s. So, for the Laplace transformation of the function f t, my transformation suppose was this one for s is greater than 0, then the Laplace transformation of E a t f t will be again the same function will be there, only thing is that it will move by a. So, it will be this value the same. So, this is my f s minus a and this is my f s. Other things will be same, it is just shifting the scale on the right hand side. So, this is sometime we also call that this property as the first shifting theorem. So, this property is also called first shifting property or the theorem. So, in this case there is no need to find the Laplace transformation again and again, I will use this property. For example, I have the Laplace transformation of cos 2t. So, that is s over s square plus 4. Now, I want to define the Laplace transformation of E 3t into cos 2t. So, now there is no need to define the Laplace transformation again and doing all this calculation. I will use the help of the first shifting theorem. So, from here I know that my f s is s over, and now I know that the Laplace transformation for this function will be f of s minus 3, because this is a is equal to 3 here, and from here I can write that this is equal to s minus 3 over s minus 3 whole square plus 4. So, whenever we are having this type of functions and this s minus something is there, then we should be understood that we are using somewhere we are using the first shifting theorem. Now, I will define another property is that what will happen if, so I have if my function L of f t is f s, then as I told you that this Laplace transformation will be used when solving the differential equation. So, what will happen when I have the Laplace transformation multiplied by some t f t. So, this one I want to find out what will be this one. So, this is given to me, but what are this one? Suppose f t is the solution of the some differential equation. So, I know that sometime the differential equation the coefficients are also a function of t, and maybe suppose I have a differential equation in which some t into f t is coming up. So, what will be the Laplace transformation of t f t? So, this one I just want to define. Now, I know that my Fs is 0 to infinity e raised to power minus st ft dt. Okay. Now, what I do is that so just call it equation number 1. So, differentiate equation 1 with respect to s. So, on the left side I will get f dash s, and on the right hand side I will use the Leibniz rule. So, I just want to take d over ds of this ft dt. So, from here I can define taking this differentiation inside. So, it is a function of s and t, and this is a function of t only. So, I am taking the derivative with respect to s. So, this will be taking the derivative with respect to s, it will be e raised to power minus st into minus t ft dt, and which can further be written as minus t. I can take minus sign, I can just take here. So, this will be 0 to infinity e raised to power minus st t f t dt. And if you see carefully, then from here I can say that f dash s is equal to minus the Laplace transformation of t f t, or I can say from here that the Laplace transformation of t f t will be minus of d by ds f s. So, this is just now we are able to define this one. So, we can use this property. So, let I take my function f t is equal to, suppose I just want to verify this one. So, let us take my f t is equal to t, and I know that the Laplace transformation of t is 1 by s square. So, this is already we know. What will happen if I just want to verify this one and Laplace of t into f t, this one I want to do. So, from here I just want to find this one. So, it will be t square, and I will use this property. So, it should be minus d over ds of f s and f s I know is 1 over s square. So, I am taking minus d by ds of 1 over s square. So, this will be what? So, I am taking d by ds of s minus 2. So, this will be minus into minus 2 over s cube. I am taking the derivative. So, from here I can define it will be 2 over s cube when s is positive, and that is all right. We already found that the Laplace of t square will be 2 over s cube. So, this is verified that whatever just now we have done, it is true. So, we can use this property to define the various Laplace transformation of the various function, just multiplying by the some t. Now, the next things we are going to discuss is, because so let us do one example that how we are able to use this Laplace transformation to solve the differential equation, because our main purpose is to solve the differential equation using the help of Laplace transformation. So, I just take a very simple example, just take y double dash plus 4y is equal to 0, y 0 is equal to 1 and y dash 0 is equal to 6. So, this is a very simple linear second order initial value problem, and this equation I want to solve. So, in this case first thing is that I have to take the Laplace transformation of the derivative. So, before solving this differential equation we should be able to find that what is the Laplace of the derivative of the function. So, let us define this one before solving this problem. What is the Laplace transformation of the function f dash t? It means I want to find the Laplace transformation of this one, where the Laplace transformation of f t is known to me and this is equal to f s. So, that is given to me. Okay. So, from here I will put the definition, I will go by definition. So, taking the integration from 0 to infinity and then e raised to power minus s t f dash t dt. Now, this is again we have to use the by parts, but only thing is that the derivative is there. So, I have to use this as the second function now and this as the first function. So, from here I will get e raised to power minus s t and integration of the second function. So, that is f t 0 to infinity minus 0 to infinity. So, taking the derivative of e raised to power minus s t. So, it will be minus s e raised to power minus s t and then integration f t dt. Now, from here I will get my function. So, this is the integration we have to solve. So, I have to define what will the limit t tends to infinity e raised to power minus s t f t and then putting 0. So, minus f 0, because this is 0 value will be 1 plus, and from here I can take my s outside. So, this will be s and then 0 to infinity e raised to power minus s t f t dt, right. So, this is the integration we are able to solve. Now, I know that my function f t is of exponential order. So, in this case, and I am also taking that s is greater than 0. So, from here now I want to solve this factor, that what will happen to this one. So, in this case now I have the limit t tends to infinity f t e s t. Now, my function f t and e s t is there. So, if t tends to infinity, I just want to check that what is the value of this function, and my function f t, if we go by the existence, this function is of exponential order. So, suppose this is of exponential order. So, it is alpha t and e s t. So, from here if you see that as t tends to infinity, this will goes to 0, because this e s t, because e alpha t I am taking and e s t is, I can say that it is taking advantage over the function f t. So, when the t tends to infinity will go, because this function is going faster than f t. So, when the t tends to infinity, this value is going very small and tending toward 0. So, this factor will be 0. So, from here I can say that my s 0 to infinity e minus s t f t dt minus f 0. So, from here I can write that the Laplace transformation of f dash t will be s f of s. So, this is a f of s minus f 0. So, we are able to define the Laplace transformation of the function f dash t. Similarly, I want to take the Laplace transformation of L of f double dash t. So, let us see what will happen in this case. So, this function is, again I am going by the definition. So, e raised to power minus s t f double dash t dt. So, this will be there, and then again applying this formula. So, e minus st the first function and then the integration of the second function minus 0 to infinity minus s e raised to power minus st f dash t dt. So, this factor is again I am putting this value. So, limit t tends to infinity f dash t e raised to power minus st. You can see from here that I am taking the Laplace transformation of f dash t or f double dash t. So, we are assuming that the f dash t is also of exponential order and f double dash also is of exponential order or maybe piecewise continuous function. So, that we should be able to take the Laplace transformation minus putting the value 0 here. So, it will be f dash 0 and then plus s, and then I am taking the Laplace transformation e raised to power minus st f dash t dt. So, this factor will again go to 0 because our exponential e raised to power minus st is going much faster than the function f dash t. So, this will be 0. So, from here it will be minus f dash 0 this function plus s, and this is already we know that this is equal to s. So, this is equal to s f s minus f 0. Just now we have calculated this value, and from here I can write that this is equal to s square f of s minus s f of 0 minus f dash 0. So, this is my Laplace of f second derivative. So, whenever we are taking the Laplace transformation of any nth degree nth derivative of the function, so in the process we always using the Laplace transformation of the n minus 1th derivative, like this one we are using here, and this is being multiplied by s. So, from here I can define the Laplace transformation of any nth derivative. So, from this one if I take the Laplace transformation of any nth derivative, then from here I can write like this one. So, it is a second derivative multiplied by s square. So, it will be s raised to power n, then function f s minus it should be s n minus 1 f 0, then next should be s n minus 2 f dash 0, next should be s n minus 3 f double dash 0 and so on. So, in the last I should get the value f n minus 1 at 0. So, this is the Laplace transformation of any nth derivative of the function f t. So, once I am able to find the Laplace transformation of the function, so now we are ready to solve the differential equation. So, just now we have defined the differential equation y double dash plus 4y equal to 0 and y 0 is equal to 1 and y dash 0 is equal to 6. So, this is my second order initial value problem. Okay. We know that with this equation we can solve very easily, as we can define the characteristics equation and then we can find the solution, and based on this initial condition I can find the value of the coefficient and then we get the unique solution. So, the question comes that why we are applying the Laplace transformation. So, this equation we are just solving to show that the application of the Laplace transformation, but later on we will be able to find the solution of those equation which we were unable to solve using the previous method. So, but if you will see that using the Laplace transformation we are able to solve quite difficult problems which was not in fact unable to solve using the previous methods. So, to solve this one, so I call it equation number 1. So, let the Laplace of function y t, so it is a function of y t here, is equal to y s. So, this is I am considering. Now, taking a Laplace transformation of equation 1. So, we are taking the Laplace transformation of the equation number 1. So, from here I can say that the Laplace of y double dash plus 4 y should be equal to the Laplace of 0 on the right hand side, and Laplace of 0 is 0, that we already know. So, and I also know that the Laplace transformation is a linear transformation. So, this can be written as Laplace of y double dash plus Laplace of 4y equal to 0. So, from here I can define the Laplace of second derivative. So, it should be, just now we have found the Laplace transformation of the second derivative of the function. So, from here I can define this, that it should be equal to s square ys minus s y of 0 minus y dash of 0. Just now we have found this one, and it should be equal to, I can write this one as plus 4 times y of s equal to 0. Now, the initial condition is 0 at 1 and y dash 0 at 6. So, that will be used here. Sometimes we are unable, we have the problem where the initial conditions are not given, then we have to assume these values to solve this equation. So, from here I can write this one as, so this become s square ys minus, I can write this as s minus, and this is 6 plus 4 ys equal to 0. So, using this one I take, just collect the terms corresponding to ys. So, this will be s square plus 4 ys, and this one I can take on the right hand side. So, it will be s plus 6. So, from here I can define my ys is equal to s plus 6 s square plus 4. Now, we know that this is the Laplace transformation. Now, I want to find the function, because the solution of this differential equation is small y t, but we got the solution. Now, if you from here taking the Laplace transformation, this was my differential equation, and once I take the Laplace transformation of that differential equation, I come up with this algebraic equation. So, that is the power of Laplace transformation, that changing this differential equation into the algebraic equation. So, here there is no derivative involved, only the algebraic value is given. So, I get this algebraic equation, and from here I am able to find my solution, but that solution in the form of ys. Now, I want to find the function y t such that this is the Laplace transformation of that function. So, I can say from here that now I want to find the value of y t. This is the, which one is the Laplace inverse transformation of the function ys. So, here there is no specific formula for the inverse, but just now we can say that we are finding the inverse of the function such that the Laplace of that function y t is ys. So, from here I can say that, so I am defining L inverse s plus 6 s square plus 4. So, from here I can write, and now L inverse, if I know that the L is the linear property satisfying the linear property. So, similarly N inverse also will satisfy the linear property. So, from here I can say, I can separate this one as s square plus 4 plus L inverse of 6 over s square plus 4, and from our the value of the functions we can say that it seems that this is equal to, so from here I can write my y t seen. So, this is cos 2t. If I take the Laplace transformation of cos 2t, this is the value, and this plus, so it coming 2 square here and 2 should be there. So, from here I can write that this as 3 multiplied by, so this one is 3 into 2 divided by s square 2 square. So, from here I can say this is equal to sin 2t. So, from here my function is, this is the solution of the initial problem, yt is equal to cos 2t plus 3 sin 2t, and that is the unique solution we were looking for the initial value problem. So, in this case we are able to solve this differential equation, but this differential equation was quite easy to solve. Even we can apply my previous method and we should be able to find the solution within the same time as we are able to find using the Laplace transformation. But we should be able to solve quite difficult problems using the Laplace transformation. So, before that I will take some advantage of the previously defined some functions. So, if you remember in the previous class we have defined the unit step function, or because whenever we in the previous classes when we were developing the theory of green functions, so at that time we have discussed the unit step function or the Heaviside function. So, I know that unit step function u t minus a, sometime we write as u a t, sometime we write as Heaviside a t minus a or h a t. So, this function is 1, its value is 1 when t is, so its value is 0 when t less than a, and its value is 1 when t is greater than equal to a. So, this is a step function, we already know with the step width is 1. So, this is we already know. Now, I will take the use of this one. So, suppose I define a function sin t into u t minus pi. Suppose I define this function. So, what is this function? So, if you see this function will be when t is less than pi, its value should be 0, and when t is greater than equal to pi, it should be sin t, because this is a function u t minus pi. So, its value will be 1. So, this one. So, in this case I can see that if I have the function sin t and suppose I want to transfer this function on the right hand side, then I will multiply this one with a step function u t minus pi and my function become this one. So, this function you can say that earlier my function was sin t like this one, and I have transferred this function on the right hand side, and now it is my, suppose I take pi. So, the function is moved from here to this side. So, in this function, the function has been moved on the right hand side. So, what is the use of this function, the unit step function? So, let us take the advantage of, what is the advantage of the unit step function? Suppose I have a function my f t, and that function is given to me in the terms of piecewise function. So, suppose this function is given to me like this one, it is f1 t, t is t naught t1. So, this is given to me. Now, then I have my function value of the function f2 t when t is greater than equal to t1 and less than t2, and suppose this is equal to f3 t when t is greater than equal to t2 and less than infinity. Suppose I take just 3 functions for this one, and now what I want to do, I want to write this piecewise function in terms of a single function. because it may have a n number of piecewise functions. So, and then suppose I want to define the Laplace transformation for this one. So, I first of all what I will do, I want to write this function as a single function. So, what I will do in this case, I can write this function as f t is equal to first value f1t. So, this one I will write like this one. Then second one I will do f2t minus f1t. So, I take the difference of this one multiply by, so here the function f1 and f2 is separated at the point t1. So, I will take the unit step function at t1. So, I multiply this one plus, then I will go further and I will take f3t minus f2t and then taking the unit step function t minus t2. So, now let us see that whether we have done the things right way or not. So, what I will do, let us take my t when t lying between t0 to t1. So, when t lying between t0 to t1, what is the value of this unit step function? Because t is less than t1, its value will be 0, its value will be 0. So, in that case I will get only value function that f t is equal to f1t. What will happen if my t is lying here? So, if my t is lying here, then I will, this value will be t is lying greater than t1 and less than t2, but it is greater than t1, it means this value will be 1 and this value will be 0. So, f1t and f1t will cancel out in that case and I will get f2t, and that is the value of the function. Now, what will about when t is greater than t2? So, this is also 1, this is also 1. So, this will cancel out by this one, this is cancel out by this one, and I will get f3t. So, if I take the value of t in the different interval, sub interval, then I will get this function. So, this is the advantage of the unit step function, that the function which were given to us in the form of a piecewise continuous form, we are able to write that function as a single function with the help of unit step function. Okay. The next thing is that, because now what I will do, I want to take the Laplace transformation of this function. So, I should be able to find the Laplace transformation of the unit step function. So, let us define the Laplace transformation of the unit step function. So, u a t, u t minus a. So, this is again we will go by the definition e raised to power minus s t u t minus a dt. Now, this u t minus a is a unit step function. So, I know that I can split this integration into two parts, e minus s t u t minus a dt. So, like this one. So, in this case when t is between 0 and a, its value will be 0. So, this interval, this integral will reduce to this form e raised to power minus s t dt, because when t was greater than a, its value will be 1. So, I can write like this one. So, from here, so if I do the integration, it will be e raised to power minus s t over minus s a to infinity. So, it is minus 1 over s and the limit t tends to infinity e raised to power minus s t minus e raised to power minus a s. So, this will get. Now, this is again this is equal to 0. So, from here I can write that this is equal to e minus a s over s. So, that is the Laplace transformation of u a t. So, we are able to find the Laplace transformation of the unit step function. So, let us see what will happen if I want to take the Laplace transformation of any function t minus a. So, that function also has been scaled as a t minus a. So, that function is multiplied by a unit step function t minus a. So, what I have, suppose I have a Laplace transformation of the function f t. So, this is given to me. and I want to define the Laplace transformation of f t minus a u t minus a. So, this is again I will go by definition. So, it will be f t minus a u t minus a dt, and then again splitting the integration, and from here I can write that this will become from a to infinity f t minus a e raised to power minus s t dt. Now, I will change the variable. Let put t minus a is equal to x. So, t will be a plus x, and the integration in this case, when t is a, x will be 0, when t is infinity, x will be infinity. So, from here this integral change to 0 to infinity, and f t minus a is f x minus s, and t will be a plus x dx. Okay, because from here you can see that my dt will be dx. So, from here we are able to define this one, then I can take this e raised to power minus a s common outside, because it is the integration with respect to s. So, I can take this and add this one. So, it is my f x e raised to power minus s x dx, and this is the Laplace transformation of the function f x. So, from here I can write that this is equal to e minus a s f s. So, from here I can say that the Laplace transformation of the function t minus a multiplied by t minus a is equal to f s. It means whenever I getting the function in the term of s, and that function is multiplied by some exponential form e raised to power minus s, it means if I need to find the inverse, that inverse will contain the unit step function. Okay. So, from here I just take one example that in the previous case I just defined what is the Laplace transformation of u t minus a. It means in this case I am assuming that my f t minus a is 1. It means I am assuming that my f t Laplace transformation of 1 and Laplace transformation of 1, I know that it is equal to s. So, that is my f s. So, if I take the Laplace transformation of this one, it should be e raised to power minus a s f s, and f s is 1 by s. So, it should be equal to e raised to power minus a s by s, and this is what we have just defined. It means that in this case I was taking the Laplace transformation of the function 1 multiplied by the unit step function. So, in this today class we were able to go further. We have solved one differential equation using the Laplace transformation, and then we have defined the unit step function, that how if a function which is given to us in the form of piecewise form, we are able to write that function in the form of a one function using the unit step function, and then we have defined the Laplace transformation of the function multiplied by the unit step function. So, in the next class we will go further and solve some harder problem using the Laplace transformation. So, thanks very much for your watching this lecture. Thank you.